one antibiotic-resistant strain, which is methicillin-resistant Staph aureus, and as you see, it's spread all over the world. And here shows that no country or no place on earth is actually protected against antibiotic-resistant bacteria, and this applies to fungi as well. And the main reason for the spreading of antibiotic resistance is the excessive use of antibiotics. They're overused, they're everywhere. You find it in animal products, in milk, in seawater, in rivers, in lakes, in soil, and microbes are exposed all the time and develop resistance. And this tells us that more than 1.2 million people die every year from strains that are antibiotic resistant. And the future is even worse because according to prediction by World Health Organization, around 2050, most of the deaths will be from antibiotic resistant strains, not from cancer as it is now. It's good news. People are not dying from cancer. Why? Because they already are dead of simple infections. And this is a very serious problem that theoretically should be faced by production of more antibiotics. And as you see, this is until 2010, there are no new antibiotics introduced and no new antimicrobials in general. And you're going to tell me, okay, it's 2010, maybe later on things change towards better. But as you see, no new classes of antibiotics and no new antibiotics introduced lately. The reasons are various, mainly financial, and also difficulties facing to introduce any kind of new classes of compounds that would act as antibiotics and antimicrobials. I will use antibiotics and antimicrobials because otherwise I would have to say antibiotics, antifungals, and when I say antimicrobials, it covers everything. In order to fight the resistance against antimicrobials, we have to get an idea of why microbes develop resistance. And this is a natural process which microbes live in an environment that is very unfriendly. And they have various mechanisms to protect themselves against harmful chemicals. And antibiotics are just one group of such chemicals. And there are several basic principles for development of resistance. It has to degrade the metabolized to the antibiotic. And this shows how strains actually increase their ability to develop enzymes which degrade the antibiotics. Another way is just to change the target, because antibiotics, unfortunately, are very highly focused. They have one target. They either aim to destroy the outer layer or the envelope of the microbes by preventing synthesis, or they affect or block particular metabolic enzymes, synthesis of proteins by binding to ribosomes, and so on. And microbes have a way to avoid that by introducing new enzymes or bypassing the blocked part of the pathway. Another way to prevent the action of antibiotics is to pump the antibiotic out of the cell, because they have innate influx pumps, and those pumps simply pump various kinds of compounds, including antibiotics. And finally, they have a way to restrict what enters the cells. The walls of bacteria and fungi are such a way designed that they selectively take only what those microorganisms want. And simply they don't want the antibiotics, they don't allow those antibiotics to cross the cell envelope. Now, how or what kind of So how we can overcome that antibiotic resistance? Well, access of the antibiotic is restricted, then the best way is to make something, a molecule that is going to diffuse freely through the cell envelope to all the membranes, the outer layers of the microbes. The efflux pumps, well, they don't pump everything. There are different classes of efflux pumps, and they recognize what to pump. This is molecular recognitions, where you have a molecule which binds by non-covalent forces to the surface of the pump to a specific receptor. And it means that the molecule that should be recognized should have particular three-dimensional space, particular charge, and so on. So it has to be, our antimicrobial should not be recognized, should not bind to any of those pumps in order to be pumped out. About destruction, it should be metabolically inert, should not be recognized by enzymes the same way of molecular recognition. And I told about the focus action of antibiotics. Our antimicrobial should actually have multiple targets, should not be focused to a particular target in the microbes. Now, the first requirement, something that can be diffused purely through the cell envelope. In contrast to our cells, microbes have a very complex structure which protects the cells. They have a lipid bilayer, which is the plasma membrane. Then they have a multi-layer of polysaccharides, which are negatively charged, and gram-negatives have another second lipid bilayer membrane. So they have two membranes in the membrane space, and again, negatively charged surface of polysaccharides, thick surface. And the same applies to fungi, for example, Candida, which causes very common candidiosis. It also has such a multi-layer structure which protects the cells. And if you look, they all have abundant negative charges. Therefore, our compound should be positively charged, and it should be amphiphilic, which means it shouldn't be only water soluble, but it should be lipid soluble at the same time. Should have both properties in order to be attracted by the negative charges, because if it's negatively charged, it's going to be repelled. And then to be able to cross both the water layers and the lipid bilayers of the microorganisms. So it must have such properties. It should not be a substrate to any of the existing and known efflux pumps of microbes, and it should not be considered harmful. So it should not resemble any class of compounds which microbes. It should not be a substrate for enzymes, should not be recognized by, should not bind to any available enzyme, which is antibiotics, which means it's metabolically inert. And there should be a selective pressure to evolve such enzymes. Now, how microbes evolve resistance? You kill 99% of the microbes by a particular agent, but 1%, few cells survive. Those few cells that survived, if they survive because they have a particular property, some difference in their structure, which allows them to grow and survive under those conditions, they will multiply, and you have now a strain which is resistant. It is not going to be killed by the same agent. And if they are not killed by our microbial, they should not be able to develop any kind of protection against it. And finally, the antimicrobial that we are looking for should not have been focused on particular metabolic pathway on one single target. It should have multiple targets. or at least it should produce agents which attack multiple targets in the cell. Okay, and in order to design anything like that, we have to start with something, and we started with tetrapyrroles. They're called pigments of life because they are the basis of hemoglobin, which is the red color of our blood, myoglobin, the red color of muscles, the green color, chlorophyll, green color of plants, and some vitamins like vitamin B12. They also are based on tetrapyrroles. And they're pigments because they have localized electrons and absorb visible light with particular wavelengths. However, you're going to tell me that, yes, but microbes actually can digest, can metabolize. They use those pigments as food, and they have even special mechanisms. Pathogenic bacteria, they use our heme for their own purposes. So tetrapyrroles are good, but they do not fulfill the criteria that we listed before. Tetrapyrroles, however, have one big advantage. They're highly versatile because we can change the periphery of those molecules without affecting the tetrapyrrole ring, which is responsible for light absorption. And by modifying the periphery of those compounds, we can introduce negative charges, we can introduce positive charges, we can have symmetrical or non-symmetrical molecules. The position of the charges can be a different place. And on top of that, the tetrapyrrole nitrogens here, they chelate various metals, and we can introduce a metal that we like, which affects their photophysical properties. So light absorption is also affected, and some other properties that I'll mention later also affected. And because I'm going to show examples about zinc chelating compounds, I put zinc here. If you look, you can very easily regulate the lipophilicity or the ability of those compounds to dissolve in water and lipids by increasing the length of those substituents. So we introduced the positive charges already because we said they should be positive. We now can modify the lipophilicity, and that tells us if we increase the number of carbons in the periphery, we get lipophilicity that we like. And up to 8 carbons here, those compounds are fully soluble in water and very well soluble in lipids. They're amphiphilic. We fulfill some of the criteria so far, and keep in mind that those molecules are not flat as they're here on the screen. They're three-dimensional, and all those substituents at the periphery, they actually rotate in space, and those molecules have a particular three-dimensional shape depending on which one of them you look at. Because they have their three-dimensional shapes, they bind, they interact with various biomolecules in the cells, and that also affects their ability to cross lipid bilayer membranes. Therefore, we can, by changing the position and the nature of those substituents, we can design three-dimensional molecules that have quite different properties. And if we take those compounds, I'll give an example only with this particular autosubstituent, because they're fluorescent molecules, and if there was a little bit less light here, you will be able to see that under confocal fluorescent microscope, they have fluorescent. They are already inside the cells. However, they're inside the cells only if they have particular lipophilicity. Have more than 4 carbons here. And this applies not only to bacteria, there's a gram-negative because they have that complex, those complex layers outside, but also to Candida and other fungi. This is how they fluoresce. And not only that, the compounds here do not change inside the cells for more than 24 hours, which means they're metabolically inert. That's what we wanted, not to be metabolized by any enzymes. If you measure the uptake, they accumulate more if you have 6 carbons, and even more if you have 8 carbons, which is not shown here. And they accumulate more in the membranes, about twice much in the membranes of those microbes, and they accumulate in the cytosol, which is also important. So far, we designed compounds that can accumulate in cells that are metabolically inert, but the cells survive, they are happy, there's nothing that happens to them unless you apply light. When those proteins are subjected to illumination, they get excited, an electron goes to a high energetic orbital, and then in a transition, which is called transition, you have spin of electron inverted, and it cannot come back immediately to this basic orbital or energy orbital because now the 2 electrons would be with parallel spins, which is forbidden, as our colleagues physicists will tell us. And in that state, the excited molecule, which now we call photosensitizer, can participate in 2 types of photochemical reactions. In type 1, the excited molecule usually takes another electron from a biomolecule, and usually the environment itself is reductive, therefore easily biomolecules donate an electron like NADH, NADPH, and you have a couple of anion radical, cation radical, and there is oxygen, which is also biradical. It has 2 unpaired electrons in its outer molecular orbitals. That's the normal atmospheric oxygen. That generates superoxide radical. Superoxide-dismutases produce hydrogen peroxide, and hydrogen peroxide is rapidly removed in microbes by catalase and peroxidases. So microbes are very well protected against type 1 photochemical reactions. In addition, the excited photosensitizer can directly transfer energy to normal triplet oxygen and convert it to singlet oxygen. And this is the most stable state of singlet oxygen. First of all, this second reaction has a rate constant that is orders of magnitude faster than the first one. Second, microbes are well protected against this kind of products, but they don't have any enzymatic protection against singlet oxygen. For billions of years of evolution, for some reason, microbes did not develop, and organisms did not develop any protection against singlet oxygen. It's reactive, reacts with amino acid side chains, which means modifies proteins, damages proteins, it damages lipids, fatty acids and cholesterol, which form the plasma membrane. And singlet oxygen also reacts very specifically with guanine residues in DNA. Therefore, it is believed that it is singlet oxygen that is the main damaging agent in such photo-induced reactions. Singlet oxygen, however, has very short half-life in biological environment, and it can diffuse only 20 nanometers inside the cells. If you look here, 20 nanometers is a very small distance, it's even smaller than the size of E. coli, which means that singlet oxygen has to be generated very close to the target, to the place where it should damage whatever is there in the microbes. This is this cell, this candida is slightly bigger, 5 to 6 microns, but definitely, even though there are publications which you can inactivate cells, microbes by compounds which take outside, the efficiency is very low. There is a way to determine production of single oxygen inside the cells using a fluorescent marker, which according to the manufacturer is highly single oxygen specific. Of course, it is not. There is no such marker. We have other means to find that single oxygen is produced. And by using, again, confocal microscopy, we can see that indeed inside the cells there is production of single oxygen, and that it is observed only if we have 6 or 8 carbons. Very little, you don't see almost anything here. When you have 4 carbons, so lipophilicity is important here. The ability to produce single oxygen correlates well with the inactivation of microbes. Here, I'm just showing one negative bacterium. And as you see, we measure 2 parameters. We look at metabolic activity and we look at ability to proliferate. And as you see here, the compounds which have 4 and more carbons inactivate efficiently E. coli, and it doesn't depend on the genetic background of the bacteria. These 2, which are red, are actually antibiotic resistant, but they're equally inactivated. Bacteria also have electron transport chain. They respire, except those that are obligate anaerobes. And if you treat such cells, you see again that 6 and 8 carbons containing compounds, or those that have quite good amphibic properties, inactivate, suppress respiration, which means that they are able to cross the outer lipid bilayer of E. coli to enter to the inner membrane and to inactivate complexes that are situated here. This is the electron transport chain of bacteria, which is very similar to our mitochondria. The compounds that I mentioned again, this is survival. How many cells are actually killed? And as you see, they kill more than 99.9% of all. And we have shown that for gram-negative, gram-positives, Candida, various kinds of fungi, they are all efficiently killed. But we haven't talked anything so far about antibiotic resistance. And there are several questions that are important to be answered here. If you want to really have a compound which can overcome antibiotic resistance. And there is a question which is very important. Can microorganisms develop resistance against those compounds, against phototreatment? Because the problem is every new antibiotic very soon leads to resistance. There's no new antibiotic that does not provoke resistance. Can they develop resistance if they are not, if they're subject to a mild phototreatment? The antibiotic resistant strain, are they sensitive to killing by such phototreatment? And do they have different way to develop resistance? And I'll try very briefly to answer those questions by using examples. Firstly, what kind of experiments were done? We subjected microorganisms to 10 or 20 cycles of sublethal treatment. It's a patient is taking a medication for some kind of superficial infection, and it follows 10 cycles of treatment, and after each treatment, there is a fraction of bacteria which survive. After those 10 cycles of treatment, you take those survivals of each cycle and you check if they're still resistant or they're still sensitive or they become resistant. And as you see, both metabolic activity and survival are equally affected. There's no difference after 10 or 20 cycles of sublethal treatment, something that, however, in antibiotics, with antibiotics, immediately leads to resistance. There's also another question that was asked by our colleagues. Okay, but antibiotics work a different way. You have a patient, the patient is treated by antibiotic for a long time, so bacteria or are exposed, or fungi are exposed to that antimicrobial for a long time, and they have time to develop resistance. While here, you just kill them in few elimination cycles and everything is gone. And what if the patient who is treated that way with our photosensitizer, after the treatment, there are remaining microbes which are not killed, and that patient is exposed to ambient light because there are traces of the photosensitizer, and therefore the microbes will be able to develop resistance. To answer that question, what we did was we were growing cells under very mild photo treatment, such a way that they can grow, microorganisms can multiply, but they're all time stressed by generation of singlet oxygen. And then we check if those microbes become resistant, and as you see, they are not. They're equally sensitive. Then we combined 10 cycles of sublethal treatment and then subjected, after we grow those microorganisms, to 10 cycles of sublethal treatment again. And finally, we check if they develop resistance. And as you see, there's no resistance developed at all under all those cycles. We also tested clinical isolates provided by colleagues in hospitals. They are resistant to different antibiotics to check if those antibiotic-resistant bacteria are resistant to photo treatment. And as you see, they are not. This is the metabolic suppression of metabolic activity. They're equally sensitive. And this is the cell killing after sublethal exposure. And when we use those clinical isolates, which are antibiotic resistant, and subjecting them to the same sublethal treatment for 10 or 20 cycles, we again saw that there is no effect on the photo killing. Doesn't matter that they are resistant to antibiotics. The two, actually, the resistance to antibiotic does not protect against photo killing. And finally, because there are some publications that show that that photo treatment affects resistance to antibiotics, we tested antibiotic resistant strains before and after treatment, photo treatment, sublethal and lethal to a level of, we have 99% of the microbes killed, just 1% or less surviving, and we grow. Their sensitivity to antibiotics remains the same. Unfortunately, we were not able to eradicate the antibiotic resistance, but they did not develop resistance against the antibiotics that they were sensitive to, and did not get the antibiotic resistance. As you see, it is the same in all those strains. And with this, what we found that we can design molecules that can avoid the barriers of microbes. They can cross the cell envelope, they can accumulate in the cytosol and in the membranes, and then they can efficiently kill antibiotic-resistant microbes by simply illumination with visible light. However, our conclusions cannot be applied to all kinds of compounds, and each compound should be tested separately because the structures that are affected, the damage that is caused by that photo treatment depends on the properties of the photosensitizers, and each photosensitizer or each new molecule has to be separately tested for development of resistance. There are publications, if you look, that some photosensitizers like methylene blue, for example, they are substrate for efflux pumps. Some are affected by the ability of the microbes to prevent uptake, but molecules that are amphiphilic and that have particular three-dimensional structure, they do not develop resistance, and this is one way to fight antibiotic resistance. It doesn't mean that they're going to replace the antibiotics. It only means that this allows antibiotics to be used only if it is really necessary, and various kinds of superficial infections can be treated with photodynamic inactivation, by photodynamic inactivation, which spares antibiotics for really conditions where their use cannot be avoided. With this, I wish to thank you and wish you success when you try to publish. I also want to thank my colleagues who worked with me developing all those compounds and testing them for various purposes. Yeah.
I saw on your picture that the dose is 44 joules per centimeter.
Yeah.
Which looks quite fine for human body. It's first. And second, how this light penetrates inside, because you eliminate something inside.
Right. Okay. Yeah. You see, we use, first of all, it's visible light, so it's not harmful. There's no effect. The reason we use that particular energy was because we wanted to kill 99.99% of those microbes. But when we did sublittle illumination, we used much lower light intensity and lower concentrations, lower photosensitizer concentrations. About the light exposure, for now, we are just thinking about superficial infections because, you see, candidiosis, for example, and staph aureus infections, acne, all that is on the surface. And what usually happens is you go to a physician, to a dermatologist, they prescribe you some kind of topical antibiotic, you put it there, after some time, everything's gone. Few weeks later, it comes again, you try the same antibiotic, and it doesn't work anymore. Well, if you do that with photo treatment, you avoid this development of resistance, because the next step is, instead of having that superficial infection, we have it internally now, and it becomes dangerous. I was surprised, by the way, that there are means now to introduce light even in the lungs and in some internal organs, because I found that there is photodynamic treatment of lung cancer, even brain cancer, and various kinds of cancers that otherwise I cannot imagine how visible light can lead to that place. Another thing is to use photosensitizers that absorb infrared light in the red area, because penetration there is deeper, but it's still not enough to go to internal organs.
Use different kinds of tetrapyrroles for different kinds of antibiotics?
Yes,
ultimately?
yes. By actually modifying the tetrapyrrole ring, you can change the absorption spectrum, the red band, instead of having it as you have in heme, for example, around 420, 430 nanometers. We can shift it to 700 nanometers, and that allows deeper penetration.
Possible to the bacteria in a way that I don't have any background in biology or genetics. Is there any way to reprogram them so that we can cure themselves or eat one another? How do you ever thought about that?
So far, no. You see, in nature,
Yeah.
how natural selection works. Okay, if organisms, doesn't matter what kind of organisms, what's their purpose? To spread genes in other individuals. If they spread their genes, they will multiply, and you have, let's say in this case, strain, which grows very well in particular environment. Those who cannot spread their genes, they disappear. So depending on the environment, there will be always a fraction of organisms which are able to spread their genes to next generation. And this is what is natural selection. Microbes which kill themselves, they will get extinct and their place will be taken by others that are more efficient in spreading their genes. So there's no way, if you kill, for example, a particular strain of E. coli, there will be another strain. If you kill Staph aureus, there will be another. If you kill all of bacteria, there will be fungi. There's no way to have empty space in biology.